Welcome back, lecture 22. We have found the derivatives of the trig functions, or at least found a method to find them, even though we didn't necessarily find all six. We've got some kind of shortcuts a little bit. We can learn them in pairs. The derivative of sine and cosine you can learn in pairs. Tangent and cotangent, learn those in pairs, and so on. We did not have time for any examples at all yesterday. So let's start with examples that use trig functions. We're forced to find derivatives of functions that involve trig functions. So this is what section is this? 3.4. Continued. So some of our work will be as simple as giving a function, and the function involves trig, and we're asked to find the derivative. So it's not really an applied problem yet. It's just kind of using the new rules to find the derivative. And we do need to incorporate new things with old procedures as well. So if we're finding y prime here, not only does it kind of force us to use our new derivative rules in terms of trig, but what else that we've already encountered? Product rule. So we've got a variable quantity times another variable quantity. So as you just said, we're going to use the product rule first. I'll just write it out, which you can avoid that step. But since it's the first example of this type, first times derivative of second plus second times derivative of first. Everybody all right with that? First. All right, so here's the new stuff, so to speak. Derivative of cosine is negative sine of x. It still is what it has always been. It's still a slope of the tangent line. It still is an instantaneous rate of change. But it's trig functions and how they're interrelated as far as derivatives. This is old stuff here. Derivative of x squared is 2x. And what is usually the question is, how much do we simplify from that point? And I think WebAssign sometimes has issues with that as far as you find the derivative and how much do you factor out in front. I would just kind of prepare to use this, even though we're really not going to use it. If I were going to use this, I would factor out an x. And I think that's about it, right? And what's left? Well, let's get this the positive term first. What would that be? 2 cosine x? Make sure when you enter things in WebAssign and Maple that you use the proper syntax, that I think they like parentheses, right, around the x. If you ever enter anything in WebAssign and it's not liking it, like you enter in a 2x and it's either browser specific or whatever, you might try 2 star x the next time, and that's an indicator that it's 2 times x. So there's our positive term, 2 cosine x, and what? Minus x sine x. So the one advantage that this form has over its predecessor here is that if we were setting it equal to 0, we know one of the solutions right away. So x equals 0 is clearly a solution. Then we could set this equal to 0. Questions on that one? Pretty straightforward. Find it, but not necessarily use it. All right, next example. Start with a function that has a couple of trig functions in it. Secant of x over 1 plus tangent of x. You'll probably use sine and cosine more. We encounter them more often. Secant and tangent sometimes have problem values. Tangent is undefined at some places. Secant is undefined at some places. So they're probably not used as much for that reason. But here's the function. And the question is, for what values, or value, of x does the graph of f have a horizontal tangent line? So we want to find the derivative.
Set equal to 0.
And you're right, set it equal to 0 because we want to know when we have a horizontal tangent line, so we want the slope of the tangent, which is y prime, to be 0. We want to find where the slope is 0. Probably not a point. It's probably a point, and then it's going to be repeated every so often. All right, I'm just rewriting the problem. So even though we have trig in the problem, what is the kind of general rule that gets us started in finding the derivative? Quotient rule. So the quotient rule, denominator times derivative of numerator minus numerator times derivative of denominator all over original denominator squared. So far we've used the quotient rule. We haven't really used the new stuff, but to finish the quotient rule, we have to use the new information that we figured out yesterday. Derivative of secant.
Secant times tangent.
That's a little odd because we're used to the derivative kind of reducing something or knocking it down. Here it kind of is more actually than what we started with. Derivative of secant is secant tangent. And derivative of 1 plus tangent. Derivative of 1 is 0. What's derivative of tangent?
Secant squared.
Secant squared. So we're probably going to want to simplify the numerator. It looks like kind of a mess because we do want to find where the slope of the tangent is 0. And we've got a fraction. What makes a fraction equal to 0? When the numerator is equal to 0. Because when the denominator is equal to 0, we've got problems, right? It's undefined as opposed to 0.
Pull out a secant.
Okay, this first expression has a secant, so does the second one. Is that it as far as pulling stuff out in front?
Yeah.
All right, if we pull a secant out in front, let's decide kind of everything that's left. So we'd have a tangent here times the 1, and a tangent times the tangent, right? Is that okay for stuff that's left in that first one? So we factored out the secant. Tangent times 1, tangent times tangent. So we factored out the secant. We're left with what?
Secant squared.
Now, I'm not thinking a lot about this tangent here, but I am thinking about possibly combining these somehow. Do we have something that will allow us to combine some tangent squareds with some secant squareds? We do, right? We have a Pythagorean identity that interrelates tangent squared and secant squared.
Right.
So let's write that down, depending on which one we want to use. Tangent squared. I have a tendency to want to keep tangent there because I've already got a tangent. So I might want to eliminate secant squared, but let's get them both. Tangent squared is what? And secant squared, tangent squared plus 1. I don't know. I don't think it's going to matter, is it? Why is it not going to matter? If I put in for tangent squared, if I put in secant squared minus 1, what's going to happen to the secant squareds? They're going to knock each other out. If for secant squared I put in 1 plus tangent squared, I'll have tangent squared minus tangent squared. They'll knock out, right? So in this particular problem, I don't think it matters. Now, in general, because I have a tangent here, I'd probably want to keep tangents around in case they don't drop out. That way I'd have an expression completely in terms of tangent. So for secant squared, let's make this substitution, although I don't think in this problem that it really matters. Remembering that everything that follows is going to be subtracted. So we're subtracting 1 and subtracting tangent squared. So we've got a tangent squared, and we've got minus 1 plus tangent squared. We do have an example problem today. I think we'll have enough time to get to it, where we've got the tangent squared of something and the tangent of something squared. So we do have to pay attention to where the squaring takes place. Do we square before we take the tangent, or do we take the tangent of that thing first and then square the result? So here you would take the tangent of it first and then square it. Here you would take the tangent of it, add 1 to it, and then square it. So we'll have an example problem that has both of those in it. So tangent squared minus tangent squared. Everybody convinced they're gone? Tangent squared minus tangent squared. So inside of here we've got tangent of x. What? Minus 1? That's looking a little better. I knew we were eventually going to have to set that numerator equal to 0. That's a whole lot better looking than it was a couple of steps ago. So where is the derivative equal to 0? Where does it have horizontal tangent lines? Don't we set secant of x equal to 0, right?
Yes.
And tangent of x minus 1 equal to 0. Does everybody understand why we don't care in this problem where the denominator is 0?
Just multiply both sides by it and it was still for 0.
Right. Or you could call 0, 0 over 1, then cross multiply. We don't even consider the denominator. We don't want the denominator to be equal to 0. Fraction is 0 when its numerator is 0. That's an interesting little problem. Somebody, well, you can't probably enter that into your calculator. I doubt if you have an inverse secant key, right?
Actually, I think they do.
I've never seen one. So if you have a calculator with an inverse secant key, I'd like to see it. It's probably a new model, like just came out this morning.
We could do
But we do have a way to change that problem around. If the secant is 0,
1 over cosine.
secant is 1 over cosine, so we would flip the secant and get cosine, and we would flip 0 and get
0.
1 over.
So 0 could be 0 over 1, right? And if you flip that, you get 1 over 0. Then the cosine would be undefined, right? Still kind of difficult to enter in onto your calculator. But I don't think we need a calculator for that. Where is the cosine undefined? Think about the cosine graph. Where is the cosine undefined?
1.
It never is, right? It's oscillating between 1 and negative 1 and is always defined. So we're not going to get a solution from that, which means that we're not going to get a solution from that. The secant is never equal to 0. We probably should, let's finish this problem and then get a quick look at what a secant graph looks like. But you'll see that the secant is never 0. So we don't get a solution from that one. Tangent of x minus 1 equals 0. So tangent of x equals 1. That's a fairly convenient value, fairly common value. Where is the tangent function equal to 1? Pi over 2? It's undefined there.
It's
Pi over
undefined,
3,
yeah.
right?
Pi over 3 would be 60. The tangent of 60 is the square root of 3, 1.7 approximately. It's one of the special right triangles. So that means it's either 30 or 45 or 60.
Is it 3 pi over 2?
That'd be,
45.
so I'm talking about somewhere between
Pi over
0
2,
and pi over
yeah.
2.
Pi over 4.
Pi over 4. Thank you.
Yeah, 45.
I knew we'd kind of
Big
get it by the
guessing
process
game,
of
yeah.
elimination. But remember your right isosceles triangle, that is basically pi over 4 or 45 degrees. The legs are the same, so you can make them 1, or they're both 2, or both 8, or whatever. Tangent would be opposite over adjacent. So tangent of pi over 4 is 1.
Yeah.
But is that the, and you could use your calculator also, that's not a problem. But I mean, some of these you ought to kind of have up there in kind of a little memory bank somewhere, or a big memory bank somewhere. That's a pretty common value. The tangent is 1 at pi over 4. But is that the only place where the tangent is 1?
No, it repeats.
It repeats, and in fact it repeats every pi radians, right? So if we're going to kind of give all the values of x that satisfy this particular equation, tangent of x equal 1, pi over 4, let's find one, we did, pi over 4, and let's tell how to get to the others. Plus pi times n, or k or something, and we want to add what kind of multiples of pi?
Integers.
Integer multiples of pi. 1 pi, 2 pi, 3 pi, negative 1 pi, negative 5 pi. So we want n to be an integer. So a common symbol is a capital Z for integer. I think that's come up in here before, hasn't it? So there are the values of x. We didn't get any from this particular piece of the equation. These are the ones we got for this one. Where's the question? Where did I write down the question? For what values of x does the graph have a horizontal tangent line? I think we found them, right? So there's our solution to this problem. Found the first derivative. That's obviously part of the problem is finding it, but we didn't stop there. We set it equal to 0 to find where that function had horizontal tangent lines. Do you think that's valuable information if you were sketching or even trying to interpret the graph of the original problem? Here's our original problem. Is it helpful to know that it has horizontal tangent lines at pi over 4 and every pi from there?
Yes.
You could see if it kind of reached a peak or reached a low point, right? At pi over 4 and every pi radians from there. All right, let's go on to the chain rule today. So let's switch to the smart board. A whole lot smarter than I am. Of course, that doesn't take much. You're supposed to say, oh, no, Dr. Griggs, you're way smarter than the smart board. No, I know better. So, chain rule. We're going to have functions that are composed functions. And we're going to do really 3 different versions of the chain rule today. Which of the 3 you happen to like the best and happen to kind of help you know what to do on these problems, that's completely up to you. But by the end of class, we'll have 3 kind of little ways or pictures or methods that you can remember to do the chain rule. So this is 3.5. The chain rule, and it's for composed functions. So not just functions of x, We're not just squaring x or cubing x, but we're squaring some function of x or cubing some function of x. So instead of x to a power, let's start with this example. I always like to start with one that we can check our answer another way. So the way we're going to check our answer is we're going to just square this and find the derivative using the power rule. But the chain rule, let's approach it the first way as a, and it doesn't, I mean, you could really approach this all three ways. Let's approach this as an extended power rule. So we've got an outside function. I think everybody would agree with this. Our outside function is the squaring function, and our inside function is the doubling and adding one, subtracting one function. So we've got an outside function, an inside function. So what we really have is something that looks like this. We've got an inside function, some f of x, and that f of x is being raised to a power. So the power rule would say that we would take this exponent, n, times the same inside function, right, to 1 degree less, and that's where the power rule ends. So we would take the exponent times the same inside function to 1 degree less. Does that look like the power rule?
Yes.
That's exactly the power rule. And then we would be done with the power rule, but this is the extended power rule. So that says we go a step further, and what is that next step that completes the chain rule?
Take the derivative of the inside.
Right, that's exactly right. Now we need to focus on what's inside, because it's not just x, it's a function of x. And we would take the derivative of the inside function. So you kind of pay attention to the outside function first, and when you're done with the power rule on that, then you pay attention to the inside function and take its derivative. So this is the so-called new part, or the chain rule part of that. So with that example that we just had, was it -1 or +1? -1. Using this extended power rule thought process, the derivative should be what? Tell me what to write down. 2, which is the exponent.
2x minus 1.
Same inside function to the first, right? 1 degree less,
What is it?
Times 2.
times
2.
2. And that is the derivative of the inside function. So let's get an answer, and then we'll check it by doing this problem another way. So the 2 times the 2, it's all product, and this is to the first. So we've got 4 times 2x minus 1, 8x minus 4.
Yes.
So we don't have an idea. I mean, we're hopefully going to be able to trust that the author's going to give us a viable method to find the derivative. And we can't always check it, but on this problem we can check it, because our original problem, being this simple, we could just go ahead and square it and then find the derivative of the trinomial that results. First term is 4x squared. It's looking pretty good so far, right? For the 8x anyway. Middle term is twice their product. And the last term is +1. So using methods that we've accumulated prior to today, just power rule and constant times a function. So we'd have 4 times derivative of x squared, which is 2x. 4 times derivative of x, which is 1. And then we'd get a 0. So I'm writing down everything. You probably wouldn't write everything down like that. You'd probably go straight to this answer, which is 8x minus 4. Same solution, right? So we at least have a general idea. We're fairly trusting that it's going to give us what we want. Let's take this same problem and approach it just slightly differently than an extended power rule. If you like the extended power rule version of the chain rule, then fine, use that as your predominant chain rule derivative finding technique. Let's take the same problem and break it down into kind of inside function and outside function. So what are the two functions we had? We had a squaring function, right? That was the outside function. And then we had an inside function, which was a doubling and subtracting 1 function. So there's our two functions. So we have y in terms of u and u in terms of x. And what we want when we're done is dy over dx. Well, we don't have y in terms of x. By the way, dy over dx is just y prime, right? Or f prime of x. Just another notation. We have y in terms of u. So we can find derivative of y with respect to u because we have a function of y in terms of u. And we can also then find derivative of u with respect to x because we have u in terms of x. Now, it kind of looks like the du's will knock each other out, right? They really don't. I mean, it's a nice little visual algebraic thing that appears. But this is a single entity right now, and this is a single entity, so we can't really mark out du over du. But it kind of helps when that is there that you'd be left with dy over dx, which is what we want. So this is that. This is probably why it has the name that it has, kind of this chaining. And if you had y in terms of u, u in terms of r in terms of s in terms of x, then you can kind of chain the whole thing out and get what you want. But we have y in terms of u and u in terms of x. What is the derivative of y with respect to u? 2u. We have y equals u squared. Derivative of u squared with respect to u is 2u. And what's the derivative of u with respect to x?
2.
We have u in terms of x, so we're deriving with respect to x. Now, this is a little bit of a problem, the fact that we would like our answer in terms of x with respect to x or in terms of x. Those are kind of synonymous. And we have an answer in terms of u. So, in fact, our answer is for u. But if you want to rewrite it in terms of x, then we just make a substitution. What is u? That doesn't sound right. What is u? That kind of sounds a little backwoodsy, doesn't it? What is u? What is u in terms of x? 2x minus 1. And that's the answer we expected, right? We did that. We got that answer with the extended power rule approach. We got it by expanding and then taking the derivative. So this is when you have kind of y in terms of a parameter, another variable, y in terms of u, and then u in terms of x, you can use this approach right here. So that could be used for if you had a whole string of equations. If you had let's say y in terms of u, u in terms of r in terms of q, and q in terms of x. Is that a chaining product that would get us what we want?
Yes.
Yeah. If you had all those equations tied up in that fashion, you can envision the du's knocking out, the dr's knocking out, the dq's knocking out, and you'd have dy over dx. So that's probably why it has the name that it has, the chain rule. You can chain as many of those together as are necessary in the problem. Now, I don't want to completely beat that problem to death, but let's make sure that everybody realizes that it was the same problem. Y was u squared, and u was equal to 2x minus 1. So if we wanted a function of y in terms of x, couldn't we take this quantity for u and plug it in here for u, right? So we could, and this is always an option on a problem when you're handed things like this in a kind of a composite format, but the composition is split out. It is the same problem that we started with. It just looks a little different because it's split out into the two component parts. Catherine?
When you do integration, this is really jumping ahead, but don't you have to use substitution a lot
Yes.
as like a form of...
Yes,
like,
and it will take an ugly-looking antiderivative.
Right.
Just talking about kind of we're reversing this process eventually, kind of the latter portion of this course. And you can look at a pretty hideous-looking integrand, and you can make it simpler looking by making a u substitution. So we'll do, it's a little different than what this is. This is kind of a composition split out format. That's trying to make something look a little bit simpler with a u substitution. All right, let's tackle this problem. So that's probably going to be our outside function, whereas before we had a squaring function. Now our outside function is a square root. And there's our inside function. And you could break it down into more pieces than that, because you've got actually in the inside function, you've got a squaring function and an adding of x function and a subtraction of 3. But let's just call all that inside one function. So if we wanted to split this out, we could have y equals the square root of u. That's our outside function. We're going to take the square root of whatever is inside, and then what is inside, there's the inside function. Now, if you substituted that quantity in for u, you'd have the original problem, right? So let's do this problem this way, and then let's kind of use this to get our third look at what the chain rule might look like, and we'll use the composed function idea, the f of the g idea. All right, derivative of y with respect to x. Since we don't have y in terms of x, we'll start with dy over du, and then we'll multiply that by du over dx. So what is that in this problem? What's derivative of y with respect to u?
1/2. Yeah.
Good.
1/2.
You can use this in the form that it's in, but for many of you that this is kind of your first encounter with calculus, you might choose to rewrite that as u to the 1/2, right? At least think of it that way before you take the derivative. And now derivative of u to the 1/2 is 1/2 u to the negative 1/2. So that's dy over du. What's du over dx?
2x plus 1.
2x plus 1. So part of our answer is in terms of x, which we want. and part of it is in terms of u, so whatever is not in terms of x, let's just make that substitution. So instead of 1/2 u to the negative 1/2, it's going to be, I'll put y prime, that's the same thing as dy over dx. 1/2 x squared plus x minus 3 to the negative half, and then that should be times what was the
2x.
du over dx, 2x plus 1.
Uh-huh.
And sometimes it's helpful, depending on what you want to do with the derivative when you're done. Right now we're just finding it, so we found it, so in a sense we're done. But if we want to use it, we might want it in a different form. What goes in the numerator?
2x plus 1.
And everything else is in the denominator, right? This 2 is in the denominator, and this is to the negative 1/2, which throws it to the denominator to the 1/2. And if it's to the 1/2, it's what, a square root?
Square root of x.
So if we were setting this derivative equal to 0, that would be a form that would be fairly easy to work with. Is that correct? How would you set it equal to 0? The numerator. When is the numerator equal to 0? And if you were seeing where it failed to exist, you'd set the denominator equal to 0. Question?
Don't you multiply by the derivative of the 2x plus 1 again? Don't you multiply by 2?
No.
No?
No, we took the derivative. This was the inside function, right?
Yeah.
And we did take the derivative of the inside function. It was 2x minus 1.
Okay.
Now, what Katie just said, that comes up when you take a higher order derivative, because it seems like you already took the derivative of the inside function. Every time you take the derivative, first derivative, second, you take the derivative of an inside function, that is the completion part based on the chain rule. So as long as you've done that once, you've done what you need to do for the first derivative. All right, let's take the third approach. Let's say that our original function is not just a function of x, but it's a composition of functions, the f of the g. Now, isn't that the same thing in a way? Don't you have an inside function, right, which is the g of x, and then you have an outside function, which is the f of x? So it's the same approach. All three of these approaches are just three different ways of getting to the same result. So in this composed function format, you would want the derivative, and this ought to match up with everything we've done to this point. If you had the f of the g of x, the f is the outside function. Wouldn't you want to take the derivative of the outside function first? Isn't that what we did with the extended power rule? Right. We took the derivative of the, not the inside piece, but the raising to the power piece. So we want the f prime. So that's the derivative of the outside function, the f function. And then you finish this by looking inside and taking the derivative of the inside function. So that's a composition of functions approach for the chain rule. If you have the f of the g, take the f prime, still leave the g intact. It stays the same in the inside function. And then the last thing you do is take a look inside and take the derivative of the inside function. So all three of those, extended power rule, that dy over du times du over dx, that format, and then this composed function format, all get you to the same result. So if we use that approach on the problem that we just had, it's plus x minus 3. Is that right? To the 1/2. then the outside function is what? The raising to the 1/2 function. Is that correct? So if we took the derivative of the outside function, it would be 1/2 times the same inside function to 1 degree less. So that's the f prime of the g of x. That's that part. And then we'd have to finish that up with the derivative now of the inside function, which is 2x plus 1. So there's our g prime. So you take your pick, and maybe all of them make good sense to you, and depending on the problem, you'll switch your method, but they all three get to the same result. All right, we've got a few examples that we can do today. And I know we have some WebAssign questions that are pending, a couple. We can get to those tomorrow. I don't think we have anything due tonight, right? But we can start class with those, or at least make sure we get to those tomorrow. Okay, let's try this one. And I would like for you to tell me what to write down. Give everybody a chance to get there first. X to the 4th. That inside function to the 55th power. And I'll tell you what, let's do. Let's go ahead and expand this to the, in fact, let's not. Okay? We would not ever want to do that. So this will tell you how much time something like the chain rule can save you. Could you imagine trying to expand this to the 3rd power or the 7th power, let alone the 55th power? So we don't want to do that. So this is a tremendous time saver. 55. To the 54th power.
Times 4x cubed plus 1.
Okay, I heard that answer a lot. Everybody satisfied with that answer? Okay, which tells you that I'm really not necessarily needed in here every day. So you guys could do this by yourselves. Would there be any necessity to raise this thing to the 54th power? No, we're not going to raise the original thing to the 55th power. We certainly don't want to raise it to the 54th power. What would we be doing with this result anyway? We would be possibly setting it equal to 0. You can do that, right? Mm-hmm. It's in factored form. So there's nothing to be gained by raising this certainly to the 55th, and in like fashion, we'll never have to raise it to the 54th either. Another thing we might be doing is throwing in a number. We might want to know what is the derivative at x equals 0. And then you could plug in 0 for x and here, and then do the computation. That's another thing. So, and then we would use our calculator if we needed it. If we're plugging in 0, we'd have 1 to the 54th. I think you can probably handle that without a calculator, I would hope. All right, everybody feel comfortable with that? Everybody got that? I heard that answer a lot. I don't see another. Let me get rid of this. Interesting little eraser. I think it likes that.
Dr. Griggs?
Yes.
I think if you do like a circle with the eraser and you tap in the middle, it'll erase everything for you.
It will?
Yeah.
Okay. See, you're smarter than I am. And you're both the board and you are smarter than I am. All right, next example. Thank you. I'll try that. I'm learning. X minus 1 over 2x plus 3, that quantity to the fifth. Now, I picked this problem specifically because these are the kind of questions that you usually ask when you're starting with the chain rule is I see a quotient here and I also see something to a power here. What do you start with? Do you start with the quotient rule or do you start with the so-called extended power rule? The power rule, because that's the outside function. Don't pay attention too much to the inside function until you've taken the derivative of the outside function. Then you need to pay attention to what's inside. So the extended power rule approach or the composition of functions approach, either one, you're going to take the derivative of the outside function, which is what? 5. Same inside function. And now that may not seem like that is a potential error place, but it is. People want to get too quick with the process. They want to take the derivative of the inside function now. That doesn't come yet. That comes at the end. So it's the same inside function to 1 degree less. Now we need to concern ourselves with the inside function, and the inside function happens to be what? A quotient. So we're going to have to take the derivative of that inside function, and that inside function happens to be a quotient. We're about out of time, but let's finish this one. So, in deriving the inside function, you realize it's a quotient, and how does that work? Squared. So, it does involve our knowing the quotient rule, but it also involves us kind of saving that till the last step of the problem and doing the derivative of the outside function first before we do the derivative of the inside function. We're out of time. We'll take that answer and simplify it completely into a form that WebAssign is going to like. See you tomorrow.